Hi kids, so today we are looking at the derivative of a function, and some of this will be familiar, so you'll feel like chapter 2 is just kind of going to roll right into chapter 3. So let's take a look and see what we have here. So we've got this warm-up where, as we discuss the objectives, where you're looking at differentiability, different ways of denoting the derivative of a function, graphing the function and the derivative, and one-sided derivatives, and graphing the derivative from data. So what we did at first is that we have this warm-up here. So if you'd like to pause your video and then try the warm-up, I'm going to just scroll down. We did go over most of these, but if you want to try 2 and 3 again, because we didn't get to those in class, then you could do so. Pause it now and then turn it back on again and check your answers. Okay, so we've got the limit as h approaches 0. So getting used to that, the h approaching 0, when you do a direct substitution, you'll get 0 over 0, which is an indeterminate form. So what we did is we multiplied, we expand 2 plus h, the quantity squared. So what you see is that the 4's cancel, and then you have eventually everything factors nicely, so you can then have a determined value of the limit, which h approaches 0s, and you get 4 plus 0, which is 4. So the limit as h approaches 0 there is 4. For number 2, though, it's a direct substitution that works quite nicely, 2 plus 3. Even though you're approaching from the left-hand side, you could still do a direct substitution. A 2 above 2 is still 2. And as you approach 2 from the right, and then we get 5/2 for our answer there. And then for number 3, you have an absolute value, so you have to understand which side of 0 you're approaching. The limit is y approaches 0 from the left-hand side. Then you've got this idea that the absolute value of y then converts to the opposite of y, because remember, if you put in a y value that's negative in that expression, which is the truth, if you look at you're approaching from the left side of 0, those are negative numbers, you're going to get a positive number, or the opposite of a negative. So we have that negative sign in front that means the opposite of y. Simplifying the expression, you have the limit as y approaches 0 from the left of -1. The limit of a constant is just a constant, one of your limit laws. Okay, so there you have it. It's -1. And then for the last one here, number 4, the answer is 8. And you can see that what you do in the top, what I'm doing in the top is that I factored 2x. You see, it's the limit is x approaches 4 of 2x minus 8 over the square root of x minus 2. And when you factor the 2 out, you get this factor of x minus 4. I'm doing that because I'm looking at something canceling, and if I put 4 in, I'm going to get 0 over 0, but I go ahead and factor the 2 out of 2x minus 8 because I want to look at that possibility of being x minus 4 in the denominator, which it is. Remember that if your limit is indeterminate, there is a factorability, a factor that will cancel, in other words. Okay, so we've got the denominator. When we multiply by the conjugate, it manipulates our expression quite nicely, and we then get our x minus 4's to cancel, and we have 2 times the square root of x plus 2, which is 2 times 4, or 8, and we have our limits. So the practice of working with limits carries over to this chapter as well. So we have then f prime of a, the derivative of f at x is equal to a. Looks like this. So now we're actually calling it f prime of a in this chapter, where in the last chapter in 1.4, we said the slope of the curve is given by that limit. And so when you come down to the graph, you can see we have our 2 points P and Q. And what we're doing is we're driving point Q down so it's right on top of point P. And instead of having a secant line that you see in black, you have the tangent line at P on the function. So that point Q, let me put it in red here, the point Q is right on top of point P on the tangent line. So as it sweeps down the curve, moving H, you want H to go to 0. So if H goes to 0, you're moving right close to A in that limit, okay, which gives you the slope of the tangent line. So as a result, then, we have the derivative of a function f with respect to the variable x is the function f prime. So now it's a function instead of having the input a. You can see if I put a here, here, and here, we have the limit definition, at the derivative at a. But now we're going to consider as x will vary and not just a specific literal constant such as a for x. This is our limit definition for the f prime of x. Okay, and so you can see that here's our first example. And so if the function is x cubed, then we've got, here's our limit definition here. F prime is equal to the limit as h approaches 0. So now we just input our function. You can pause the video at any time. We input our function x cubed, but it's x plus h cubed minus x cubed over h. And then after that, we expand the x plus h cubed. And notice at this step, then we cancel the x cubes, factor out the h in this last step, factoring out the h and canceling it, and then taking the limit by direct substitution. And we get 3x squared. Now, some of you who've worked ahead are like, oh, that's the derivative of x cubed, which it is. And we just did that, right? So this is the limit definition of the derivative. So there is also the alternative, using that h approaches 0 is not the only limit that we can use to find the derivative. We have the definition or the alternative derivative at a point where we take the derivative of f at the point x is equal to a, and we have this limit. So we have f prime of a is equal to the limit as x approaches a of f of x minus f of a over x minus a, provided that the limit exists. So if you look at your limit here and you have the slope of the tangent line, same as the last diagram, except we're using different notation, where that point Q is x f of x and point P is a f of a, and we're driving x. It's going to be the limit as x gets really close to a, so it's right up close to a there. And you can kind of see in my definition over here, I could put absolute value here, but if I take x minus a, x is in my diagram larger than a, and f of x is larger than f of a. So if I subtract them, I'll get a positive delta x and delta y. Okay, so there you have that. And then differentiate the function f prime. Now that means, differentiate means to take the derivative of that function. Now some of you are thinking, well, this is x to the 1/2 power, and you know something called the power rule because you've been working ahead. But let's stay with this because you need to recognize this f prime of a as the derivative being a limit. So it is 0 over 0 form when we set this up, because if we put a in here and here, we're going to get 0 over 0. So the first step, we set it up, right? This. And then we notice it's 0 over 0. But we have that conjugate manipulation. So we're going to multiply by the conjugate over itself. So multiply by square root of a, square root of x plus square root of a over square root of x plus square root of a. We are rationalizing the numerator, which is kind of interesting that students aren't usually used to that. But we do that so that we can manipulate our expression to get around the whole removable discontinuity issue, right? We can still deal with the limit then. So as we go through the limit, we get 1 over square root of a plus square root of a, 1 over 2 square roots of a. And as you go forward, when you have f is equal to the square root of x, you're going to notice that f prime is equal to 1 over 2 square root of x. And it'll be a very common derivative for you to take. Okay, and so then here are common ways to state derivatives, as we said. Y prime, dy dx, or the derivative of y with respect to x. Df dx, not used as much, but is used sometimes. The derivative of the function f with respect to x. And then the derivative with respect to x, we're taking the derivative with respect to x. So this is what we call an operator in math. We're going to take the derivative of f of x there. Now, if we ever use d over dx, it doesn't mean the derivative. It means you're going to take the derivative and you're going to have something in next to it, like a function. Then there's this last one, f prime of x. And this is what's known as Lagrange notation, whereas this notation here is very popular. That's Leibniz notation. Leibniz notation. But we'll talk about those two guys. Leibniz was the German who took some of the credit for calculus, and Newton was the Englishman that took credit for calculus. So what we want to do is sketch the function f prime of x, given the f of x is equal to x squared minus 3. So what I want to do is kind of approximate the slopes. And you can see that I have tangent lines here from -2 to 2 and approximated the slope of each one of those. So remember that a tangent line shows the behavior of the curve around that point. So you can see that I have some highlighter on there, right? So I'm looking at 2 and -2, and it appears that the slope is 4 and -4. Oh, don't have the negative sign in there. -4 and 4. Come on. Okay, so -4 and 4. All right, 1, 2, and let me put that negative sign in like that. Okay, so, and then at -1 and 1, the slope appears to be 2 and -2, or -2 and 2 respectively. And then you can see at 0 that the slope or the derivative is equal to 0, or there's a horizontal tangent line there. So you can see that the slopes go from negative, pretty negative, to less negative, and then to 0, and then to positive and more positive. Okay. So when we come down here, what we're going to be doing is we're going to graph the function, which is f prime. F prime of x is another function. And you can see that the function itself, f of x, I left that on the graph. There's f of x. And then let's graph the points that we saw in our table where we have independent variable from -2 to 2, and the dependent variable is now being graphed as f prime of x, the f prime of x values that we got from estimating the tangent line slope. So what we're going to do is then connect these points once we put them on the graph. We're going to connect them, and this is our graph of f prime of x, okay? Now you can see I have these two notes off to the side. If f prime is greater than 0, it's above the x-axis. If f prime is less than 0, it's below the x-axis. You can see where I have this point where the slope is equal to 0. On here, f prime is equal to 0 from above. That goes directly to the point 0, 0. So the slope is 0, and you can see that the slope is positive up here, and the slope is negative down here. Okay, so just one example of doing that. Now, if we take the next example, we want to sketch the graph of the function f of x on the graph to the right, whose graph of f prime is, here, let me write the f here, f prime of x is to the left. Now this is kind of an easy one. You don't want to go crazy with things, but you can see f of 0, if you look at this value, f of 0 is equal to 0. The graph of f prime is given below. I have a typo here, I'm just checking it. Okay, so the graph of f prime is given below. So if I look at this, I've got the slope y prime is equal to f prime of x. So if I look at this graph and I want to go back, I want to graph the function. Here I want to graph y is equal to f of x. Now, I have to have the information f of 0 is equal to 0 because I'm going from, this is your f prime graph, and I want to go to f of x. So let me take some white out and get rid of this. This will be the last example I'm going to do on this video. So I'm going to take the white out here, wipe that out. So I want to graph f of x to the right. So now I'm going to start at 0, 0, right? So now I know f of 0 is equal to 0, but I want to go to the rest of them. I want to say, okay, if that's equal to 0, I need to get some values here, right? So this value is y is equal to 1. Now remember, this is f prime is equal to y is equal to 1. Now I'm using y in a different way. So, and then I have f prime is equal to y is equal to -1 over here, right? So that's giving me the idea of the slope. So it seems like everything is changing at x is equal to 1. So I know f of 0 is 0, but then I have to go to 1, right? And everything is going to kind of change. So I'm going to put a highlighter there, and I'm going to say, all right, something happens here. Oh, I wanted a highlighter. Undo. Go to the highlighter pen, and let me just put it right like that. Okay, so I know f of 0 is 0. And then now, let me go back to the pink, do a pink graph. So I know the slope is -1 to the left of 1, all the way up. And then it's 1 to the right of 1. See, here's 1. I'm going to draw a line here. So let's see if we can draw this. So as things are going to divide there, I'm going to draw a line that has a slope of 1. So it's I get 2 points to go through, right? So I'm going to go like that. But I'm going to stop when I get to 1. Now, I might have to back things up a little bit here, but we'll do that when the time comes. And then the slope is 1, so I'm going to go through the point 2, 0. And I think it looks all right there, okay? It looks like I have a slope of 1 there, right? Now, something happens here at 1, so I need to kind of back it up just a little tiny bit here on the right and on the left so that I can appropriately show you that I've got a hole right here. At 1, there's a hole on the function. Oh, there's not a hole. What am I doing? There's a point there. There's not a hole. Sorry. For a second, I was going the other way, thinking, oh, this is the derivative, but there's not a hole. This is the point 1, -1. What doesn't exist is the slope there. The slope, f prime dn's, does not exist at x is equal to 1. Okay, so we know it doesn't equal, the slope doesn't exist there because the slope is a limit. So remember that if you have the limit as x approaches 1 from the left, right, it has to equal the limit as x approaches 1 from the right. But keep in mind, I'm telling you that slope is not this function. Slope is the left-hand function that you see there. So if I take the limit from the left, I'm going to get -1. If I take the limit from the right, I'm going to get the 1. So this is a corner, and slope will not exist at that corner. It is a two-sided, slope still has to be, so here they're not going to be equal. Slope must be a two-sided limit since it is a limit. Okay, so I'm going to stop right here. We're going to talk about one-sided limits and then see how things go with that. And that'll be a wrap for this section. We're in Chapter 2, Section 2.1, moving forward.